We're surrounded by the language of chance every single day. The weather forecast, a doctor's opinion, the odds of your favorite team winning. But what's really going on behind those numbers? Well, in this explainer, we're going to build the foundational toolkit to really understand the world of probability.
We hear things like this all the time, and we make decisions based on them. Do I need an umbrella? Should I cancel the picnic? We use probability constantly, but how many of us can actually explain the system that comes up with that number? To do that, we have to start with the basics.
All right, first things first, we need to learn the basic vocabulary. Think of these next few ideas as the core toolkit you need to talk about probability like you really know what you're talking about. Okay, first up is the idea of a probability experiment. Now, this sounds super technical, but I promise it's incredibly simple. It's just any action where you can get a specific result. Rolling a die, flipping a coin, even asking someone a question in a survey. Yep, those are all probability experiments.
And when you do one of those experiments just one time, the result you get, that's called an outcome. So if you roll a die, the outcome might be a 4. If you flip that coin, the outcome is either heads or tails. Simple as that.
So the sample space is just a complete list of every single possible outcome. For a coin flip, the sample space is just heads, tails. For a regular 6-sided die, it's 1, 2, 3, 4, 5, 6. It's the entire universe of what could possibly happen.
An event is the specific thing we're actually interested in. It's a piece of that bigger sample space. For example, rolling an even number is an event. An event includes the outcomes 2, 4, and 6. And that's a key difference. An outcome is just one specific result, but an event can be a whole group of them.
So let's pull all 4 of these ideas together with this one easy example. The experiment is just rolling the die. The sample space is all 6 of those possible numbers. An event we might care about is rolling an even number, which covers the outcomes 2, 4, and 6. And if you roll it and a 2 comes up, that specific result is your outcome. See how they all nest inside each other? It goes from the general action right down to the specific result.
So we've got the language down. But what happens when things get way more complicated than just a single die roll? We need a way to map out all the possibilities, especially when the numbers get huge.
A really great tool for this is something called a tree diagram. Let's take blood type. You start with the 4 main types, O, A, B, and AB. Then, from each of those, you make new branches for the RH factor, either positive or negative. Just by following the branches, you can clearly see all 8 possible combinations, from O positive all the way to AB negative.
Now, tree diagrams are fantastic, but you can probably see the problem, right? They have their limits. What if you're trying to figure out all the possible options for a new car, or all the passwords you could create? You would run out of paper fast. We need a more powerful tool.
And this is where the fundamental counting principle comes in. Honestly, think of it as a superpower for calculating possibilities without drawing a single thing. The logic is so simple. You just multiply the number of options you have for each step in a sequence.
Let's use this on that car buying example. You've got a series of choices to make. First, you pick from 3 different manufacturers. Then, for each of those, you can choose between 2 car sizes. And finally, you select one of 4 colors.
So, how many different cars are possible? Using the fundamental counting principle, we just multiply the options. 3 manufacturers times 2 car sizes times 4 colors, which gives us a grand total of 24 unique combinations. Way faster than trying to draw that tree diagram. Okay, now that we can count all the possibilities, let's look at how we actually calculate probabilities. It turns out there are really 3 main ways to do it. 3 different lenses for looking at the world of chance. And each one exists because, well, the world gives us different kinds of information to work with.
First, you've got classical probability. This is the stuff of textbooks, the world of pure theory. We're talking fair coins, perfectly balanced dice, raffle tickets. Whenever every outcome has an equal shot, the probability is just the number of ways you can win divided by the total number of possibilities.
But life isn't always perfectly fair and balanced, is it? And that's where empirical probability comes in. This isn't based on theory. It's based on observation and real-world data. You run an experiment or you conduct a survey, and the probability is simply how often something actually happened.
This survey on reading habits is a perfect example. We can't use classical theory here. Instead, we have to look at the data. Out of 1,490 people they talked to, 578 said they only read print books.
So the empirical probability that the next person you ask reads only print is 578 divided by 1490, which comes out to about 39%.
And the third type is subjective probability. This is what we use when we don't have perfect theory and we can't run a repeatable experiment. It's based on expertise, intuition, and educated guess. When a doctor gives a patient a 90% chance of a full recovery, they're using all their knowledge and experience to make that estimate.
So we have this perfect theory on one hand, and then we have this messy, real-world data on the other. Is there any way to connect them? The answer is yes, and it's actually one of the most important ideas in all of statistics.
It's called the law of large numbers. Think about it like this. If you flip a coin just 10 times, you might get 7 heads. That's an empirical probability of 70%. But if you flip it 10,000 times, your result is going to get much, much closer to that theoretical 50-50 split. In short, the more data you collect, the more reality starts to look like the theory.
Okay, we have the vocabulary, we have the counting tools, and we have the different types of probability. So let's put it all together with one final, pretty large-scale example. Imagine you need to guess an 8-digit student ID number. Each digit can be anything from 0 to 9, and numbers can be repeated. We can go straight to our fundamental counting principle. There are 10 choices for that first digit, 10 choices for the second, 10 for the third, and so on for all 8 digits.
When you multiply that all out, the total number of possible ID numbers, our entire sample space, is a staggering 100 million.
And since only one of those combinations is the right ID, this becomes a problem of classical probability. Your chance of guessing it correctly on the very first try is just one single chance out of 100 million.
So from a simple coin toss to a 1 in 100 million shot, the rules of probability give us this incredibly powerful way to make sense of uncertainty. Which brings me to the final question, and this one's for you. Now that you have this toolkit, where are you going to see the language of chance at work in your own life today?